All right, welcome back to Math 160. We are going to finish our Unit 4, Unit 5 notes so that on Wednesday's class, we can move right into Unit 6. So let's take a look. I wanted to add a couple things to practice number 10, just to make sure that we're okay with calculating binomial probabilities, especially by hand. So for instance, with problem number 1, I wanted, practice 10 part A, not problem 1. I wanted to rewrite this form where finding the probability that x is equal to 4. I wanted to rewrite that in binomial form for you. So remember that in calculating the probability that 4 offspring peas have green pods, you are going to take the 6 that you had total, n is 6, you're going to do 6, choose 4. The probability of success is 0.80, and we want 4 of them to have the green pods, while we want the other 2 to not have the green pods. So if you had typed this into your calculator, you will get 0.24576. For part B, and the reason I'm showing you this is because you're not always going to have access to that online software. So I wanted to make sure that you were okay with this. For number 2, no more than 5 meant 0, 1, 2, 3, 4, 5. I know you're not going to want to calculate the probability of each of these 6 values. So instead, we are creative with it. We say, well, the probability that x is less than or equal to 5, that's going to be the same as 1 minus the probability when x is 6, right? It's what's left over. Out of those first values from 0 to 5, the 6 is the only one that's not included. So probabilistically, we know that total probability is 1. So if we subtract the probability of 6 from 1, then it gives us the probabilities from 0 to 5 inclusive. Okay, so essentially you go through this exact same process. Remember the probability of x equaling 6. You're going to take this part and you're going to say, all right, well, 6 choose 6. You want, for the probability of success, you want all 6 of them to be green, which means you want none of them to be other than green, right? So 0.20 to the 0th power. Once you find this probability, subtract it from 1, you'll notice that you end up getting 0.737856. Okay, for part C, I would still do that by hand. I would add the probability of 0, 1, and 2. I would just do that together. Since it's actually fairly straightforward, you would have to calculate the probability 3 times and simply add those together. Okay. Any questions on number 10 and me reframing those probabilities for you? Okay, and in which case, you know what, let me write this out as well. Just this part of the formula, that you would take the probability of 0, you'd add it to the probability of 1, and you'd add it to the probability of 2. That's all you're doing. You'll take those 3 probabilities and you add them together. Good. I want you to feel confident and comfortable with calculating binomial probabilities. Turn the page when you're ready.
Sorry, I'm not ready.
No, that's okay. That's okay. I wrote down a lot. Whenever you're ready, you will have to calculate binomial probabilities in Lumen. I would urge you to try to do as much of this by hand or using the table, as opposed to going straight to the online software, but it's only for you to be confident with that formula. So I urge you to try to use the formula, okay? That's going to be important. All right. Beautiful. I'm going to turn the page. Number 20. Page 20, excuse me. I can't even talk. It's okay. That formula sheet that you all have, this is another set of formulas that you need to include on that sheet, okay? we are going to add the mean and the standard deviation of a binomial distribution. So these formulas here, I would like you to write on that formula page. Now, remember, you shouldn't give it a label. Please don't just write mu is equal to n times p or sigma is equal to square root of n times p times q. Don't just write that. You need to give it a header. So the mean and standard deviation of the binomial distribution. Okay. Remember that mean refers to the expected value. N is the number of items you have in your set, in your sample. P is the probability of success, and Q is the probability of failure. All right, the mean and the standard deviation. So let's try this out. First example, the manufacturer claims that in a shipment of 125 television sets, keep that in mind, that's telling us that our shipment contains 125 items, which refers to N. Labeled that N. We're told 98% of the sets will be operative. So that means the probability of success is 0.98. What's the probability of failure?
2.
Yes, 2%, which we'll be writing as 0.02. Be very careful with those decimals as you write those down. We're going to determine the mean and the standard deviations by simply using the formula. To calculate the mean, you're going to take the total number of items in your set and you're going to multiply it by the probability of success. So go ahead and take your calculators and multiply 125 by 0.98. I'm going to grab my calculator as well and do the same thing. When you have the result, please share with everyone. Who punched it in? Go ahead and share. Yes, thank you, Ho. 122.5. Sharing in the chat is awesome too. Thank you, Holly, because I can see it, right? So as soon as you have it, you can share it in the chat or you can share verbally as well. It's completely up to you. Next, we're going to calculate the standard deviation. We see that it's the square root of the product of N, P, and Q. Be careful. So you want to multiply everything first, then take the square root of that value. If your calculator allows you to punch everything in as an entire expression, then please do that as well, whatever works. When you have your final result, please share. And round to the nearest hundredths place. Let's round to 2 places after the decimal. How about that? Thank you, Abby. That's perfect. 1.57 is correct. Next, we want to explain what the expected value means. Now, consider we're talking about television sets. So mu is 122.5. Because we're talking about television sets, we can't have half of a television set. Nobody would buy that. So here's how we can write down what the expected value means. So, and remember, we're referring to whether or not it's operative. So in a shipment of 125 TVs, I hope you don't mind me abbreviating, I mean, why not? In a shipment of 125 TVs, we can expect that approximately 122 TVs will be operative. Okay, remember, we're talking out of 125. So technically in any shipment of 125 TVs, we can expect that about 122 of them will definitely be operative. where we're expecting about 3 to possibly be non-functioning, unfortunately, which makes sense because only 98% of the sets will be operative, typically.
Could I ask a question?
Of course.
Where did you get the 122 from? Did
So
you subtract it from? Sorry, you go.
no, that's okay. So when we think of expected value, I want you to think of mean. So when we calculated the mean, mu, we found it to be 122.5. And I'm going to write this here. So this is the mean, which is also the expected value. So that's 122.5. I rounded down because we can't have half of a television set, but I also didn't round up because we don't actually have 123 complete working sets, but we do have 122 of them. So that's why I cut off that change, Donna, to make it more applicable to what we're doing, instead of just saying 122.5. The 0.5 doesn't quite make sense.
Okay.
Awesome. Awesome. And yeah, it's based on our value for the expected value or the mean. Same thing. Beautiful. Great question. Next, we want to determine the maximum and minimum limits for usual values. Who remembers the formula for the max and the minimum limits for usual values? I know you do.
It's the mean plus 2 times the standard deviation for the maximum, right?
Yes.
And then
Excellent.
for the minimum, it would be the mean minus 2 times the standard deviation.
Perfection. Very, very nice. Let's write that out. Beautiful. I love that. At this point, I really do want this to just be kind of like something that you'll always remember, right? To find the minimum usual value, mean minus twice the standard deviation. The max is going to be the opposite, where you're adding. Beautiful. So we're simply going to plug into this formula. We know that the mean, which we calculated, is 122.5. So for the minimum, you're going to do 122.5 minus twice the standard deviation. We calculated the standard deviation to be 1.57. It's right here in part 1. So we're going to use this 1.57. For the maximum, we're going to do the same thing, except we're going to add instead of subtract. So 122.5 plus 2 times 1.57. When you punch this into your calculators, please share either verbally or type it into the chat. What is your range of values? What's your min, comma, what's your max? I would like your min and your max. And let's round to 2 places after the decimal. If you have to round, you may not have to.
For the min, I got 119.36.
Yes, perfect. 119.36. Exceptional. What's the max?
125.64.
Yes, perfection. Thank you, Emma. And thank you. I see that in the chat as well. Good. I'm going to write the range in interval notation just so that we're used to this. So in interval notation, your range of values from low to high is 119.36, comma, 125.64. So this statement indicates the following. It would be unusual. Sometimes I like talking about unusual versus usual. In this case, I'm going to talk about unusual so that we can refer to the number of TVs that would be inoperative or malfunctioning that is either below this value or higher than the max value. So here's what I mean. So it would be unusual to have less than Now, I want you to keep something in mind before I write a number down. Let's answer this question. Is 119 TVs within the usual value boundary? Is 119 TVs within that boundary?
No.
No, it's not. Okay. 119 is not in this boundary, but 120 is. Does that make sense? 119, I'm going to write this super, super tiny. 119 and lower is outside of this boundary. I hope you can see that 119. It's mad small, but it's there. So 119 is smaller than the lowest value. Is 126 within this boundary?
No.
No, of course. So 126 and bigger is outside of those bounds. So it would be unusual to have less than 120 TV sets or TVs. We could say just TVs. It would be unusual to have less than 120 TVs or more than 125 TVs be operable in a shipment of 125 TVs. Okay, which actually makes sense. This shipment is literally 125 television sets. So it'd be unusual to have less than 120 or more than 125 TVs. More than 125 being all of them, that's going to be unusual. Okay, so any more would be unusual. You could have rephrased this. It would be unusual to have 119 or less, right? Because you're including that be unusual. That would be totally cool as well, because you're including that 119 value. But you can totally just take care of that by saying less than 120 TVs. Because that is what that implies. It doesn't equal 120, it's less than 120. Oftentimes, it's going to be helpful to think about the values that are outside of this range before you actually write your accompanying statement. Beautiful. What questions do you have for me? Hearing none, let's try this again. Go ahead and turn the page. We have practice number 11. Okay, according to the Office of Disease Prevention and Health Promotion, as of 2020, at any one time in the United States, 1 out of every 25 hospitalized patients are affected by a healthcare-associated infection. The records of 15 randomly selected hospitalized patients are examined. I would love for you to tell me what information you know right off the bat. So just give me one piece of info. What do you see?
1 out of every 25.
Interesting. What does that refer to? 1 out of 25. What is that?
Of the hospitalized patients that are affected by the healthcare.
Yeah. What does that value? Hey, chill. What does that value 1 out of 25 even represent? That is totally true that we need to hone in on that. What does that sound like? Remember, think about this as our binomial distribution. We need an N, we need a P, we need a Q. What do you think that 1 out of 25 represents?
I try.
P.
The P are probability of success. Yes, okay. So 1 out of every 25 are affected by a healthcare associated infection. Even though that sounds like, oh, who would want that? That's still considered our P value, our success. So I'm going to write it like this. So P is equal to 1 out of 25. But I am going to convert this to a decimal. So 1 divided by 25 gives us 0.04. So we see that what that implies is that only 4% of patients are actually affected by a healthcare associated infection. Cool. So what are the chances that that does not happen? Give me the decimal form, please.
96.
Yes, 96% or 0.96, perfection. Now we have P, we have Q as well. Good. I have one more piece of information that I need. And what is that? What do you see?
Could you ask again? Sorry.
Yeah, no, that's okay. Looking at just the word problem here, what's the last piece of info we're given? Ah, Emma, yes, Ava, excellent. So the ladies are saying what we're told is that we are choosing 15 randomly selected patients. That implies our N is equal to 15, okay? 15 randomly selected patients. So that's our N. Good. We're going to determine the mean and the standard deviation. We know that the mean is calculated by taking N and multiplying it by the probability of success. And you know that the standard deviation is found by taking the square root of N times P times Q. Go ahead and calculate both the mean and the standard deviation. When you have both of those values, please share them. For the standard deviation, give me your answer to 3 places after the decimal. For the standard deviation, give me to 3 places after the decimal. Double check that. Double check what you have.
Would it be 0.6?
Yes, 0.6 is our mean. So we have 15 times 0.04. We find that is 0.6. What about our standard deviation? Thank you, Emma. Thank you, Ho. So thank you for providing the solution, which is 0.759. 0.759. If you want, double check this, make sure that you're punching this in, okay? I would actually just type in, you could do square root and then use parentheses again, just to make sure you're really packaging everything underneath that square root. And then I type in 15 times 0.04 times 0.96, then close the parentheses. And we see that to 3 places after the decimal leaves us with 0.759, okay? So 0.759. Be very careful with how you plug this in. Good. So explain what the expected value means. Remember that the expected value refers to the mean, which is 0.6. Now, again, this is kind of a strange statement to make because we have a value of 0.6. We also know that technically you can't have 0.6 of a person. But here's how I'm going to write this out. Okay. So we would expect .6 patients to have a healthcare associated infection. While hospitalized out of a randomly selected group of 15 patients. We would expect 0.6 patients to have a healthcare associated infection while hospitalized out of a randomly selected group of 15 patients. This one's interesting because we can't quite say that we would expect one patient to have a healthcare associated infection because we don't have a full patient. We have 0.6. And I know you're thinking, but you can't have 0.6 of a person. But I'm kind of uncomfortable rounding up to 1 because we don't have that value. So essentially, by using that language, 0.6 patients, we're basically indicating that it is pretty unlikely that this would actually happen. Okay, it's pretty unlikely that in a group of 15 patients, you would have someone with a healthcare associated infection. It's pretty unlikely. Okay. And I can actually add that. I just want to add this note for you. I'm going to say it is pretty unlikely. We want to determine the maximum and minimum limits for usual values. You know what those formulas are. For the min, take your mean and subtract twice the standard deviation. For your maximum, take your mean. Oops. Let's try writing it correctly. For your maximum, take your mean. That's what I get for writing and talking at the same time. And add twice the standard deviation instead of subtract. Use the values from above. We calculated the mean, we calculated the standard deviation. So we have 0.6 minus 2 times 0.759. And then we have 0.6 plus 2 times 0.759. When you have your min and your max, would you please share that with the group? Your minimum value is?
I don't know if I'm right, but negative 0.918.
Yeah, perfect. Negative 0.918. You're probably already thinking about the fact that you can't have negative people. And it's okay. Remember, it's just a mathematical computation. And we know that when we think about using math to model real world examples, there's typically going to be a domain that exists in the real realm, right? In the real world. Outside of that domain, it doesn't quite make sense. Like a negative 0.918, that doesn't quite make sense, but we can interpret what this is saying. Yes, Leah, your upper bound is 2.118. Thank you for writing it as in interval notation. So if you can see in the chat, Leah wrote it in interval notation. So negative 0.918, comma 2.118. We can talk about unusual values or usual. So here's what I'm going to start with. I want you to think about the fact that we're talking about people, right? We're talking about people. So do you agree that 0 patients is in this range? 0 patients falls within this range. 0, 1, 2 are all within this range. Okay. So 3 or more fall outside of this range, right? 2 is within, 3 is outside. So let's talk usual. It would be usual to find that 0 to 2 patients would have an infection. I hope you don't mind me dropping the healthcare associated infection. We know what we're referring to at this point. So that 0 to 2 patients would have an infection out of a randomly selected group of 15 patients. We can expect that, like it would be usual. I'll use that language. It would be usual to find that 0 to 2 patients would have an infection out of a randomly selected group of 15 patients. What would be unusual is to have 3 or more. That would be unusual. Then we can imply that somebody's cutting corners, or maybe they're not following protocol. Something's going on that's not right. I'm going to add that one statement. It would be unusual to find 3 or more patients out of a group of 15 randomly chosen patients to have an infection. And remember, we're referring to a healthcare associated infection. It would be unusual to find 3 or more patients out of a group of 15 randomly chosen patients to have a healthcare associated infection. Beautiful. Any questions for me? We only have one more, and this last one is for you completely on your own. One of the comments that I would like to make is the following. Before you look at practice number 12, can you look at my descriptions for each of these? Look at the description for the mean. Look at the description for your usual values for this problem, and also for our previous problem. What do you notice is included in each of these answers, in each of these write-ups? What's included? What do I keep repeating?
Whether or not it's likely or unlikely.
True, good. Tell me more. There's something else that I keep including in each of these descriptions.
Whether it's unusual.
A little bit more than that. And look at our previous one too.
I keep saying the word unusual, but maybe that's just me.
Well, so unusual, you'll definitely use that language for when you determine your max and your min, you have to use that language. It's definitely associated with it. But there's something else that is in each of my answers. Can you read each of the descriptors here? Yes, Emma. Okay, check this out. Emma just said you use the N value in a shipment of 125 TVs. Do you see that that was our N? It would be unusual to have less than 120 TVs or more than 125 TVs be operable in a shipment of 125 TVs. Okay. For problem 11, look at B. Blah, 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 out of a randomly selected group of 15 patients. For part C, out of a randomly selected group of 15 patients. That language is here. We see that N was 15. That language is in your word problem itself. So what we're noticing is that when we actually write out our description of what the mean or the usual values actually represent, we always refer back to the number of items in that randomly chosen group. You always want to use that language again, because it's not like it's out of 100, out of every 100 patients, right? Out of every group of 100. No, it's out of every group of 15. So you want to be really specific in that regard with your answers. Having said that, I'm going to pause the video and I would love you all to try practice number 12. All right, so we find that for this survey, 79% of all Americans have a cell phone. So this is the probability of success, right? What is the likelihood that Americans will have a cell phone? Well, according to the survey, 79% of them will have a cell phone. So if you think about it this way, remember, what's the opposite? If they have a cell phone, the opposite would be that they don't have a cell phone. If 79% of all Americans have a cell phone, then 21% of all Americans will not. That's how I want you to move through this problem when you try to think about your P and Q. What is success, right? What's the likelihood of something happening, and what is its opposite? Remember that binomial means two particular outcomes. So when we look at this, we think yes or no, has it or doesn't have it, right? You want to think of that kind of two possibility progression through a problem like this. So either they do have a cell phone or they don't. The US represents the 4th highest country for smartphone to population data, with Apple being the leading brand. That's just a fact, right? That's just a fact found from a 2020 survey. By the way, this data is actually accurate. I pulled this information from reputable sources. You're then told a sample group of 23 people were randomly chosen. This is really, really important to note because that represents our N. So N is equal to 23. So we're going to start off by calculating the mean and the standard deviation. We know this is going to be N times P. So we have 23 times 0.79. At this point, it's just plugging into the formula. So we find that the mean is 18.17. I just rounded to 2 places after the decimal. If you left it to 3, that's totally cool as well. No big deal. You then want to take the square root of N times P times Q to find the standard deviation. If you are using, something other than a calculator, like an actual calculator, you may want to punch in everything underneath the radical before taking the square root of the value. So 23 times 0.79 times 0.21, enter, and then take the square root of that value. When all is said and done, you should have something very, very close to 1.95. It might be a little bit longer than that, depending on how many places after the decimal you've included. We then want to explain what the expected value means. So we can say, we would expect approximately, now notice that our mean is 18.17. So in this case, I'm actually very comfortable saying we would expect approximately 18 Americans out of 23 randomly selected Americans to have a cell phone. Good. We're specifically looking at just our value for the mean, 18.17. We know that 19 of them is too high, but 18 is more accurate. So we could say 18.17 Americans out of 23 randomly selected Americans would have a cell phone, or we can be a little bit more realistic and say that 18 would be an appropriate value since you can't have 0.17 of a person. Okay, I do know with our previous problem, we had 0.6 and we weren't comfortable rounding up to 1 because it wasn't a full individual, full patient that would contract the healthcare associated infection. For part C, determine the maximum and minimum limits for usual values. This is the exact same process. So for your mean is 18.17, and you're going to subtract twice the standard deviation. And then for your max, do the same thing. 18.17, but this time add twice the standard deviation. You should find that for your min, you had 14.27 approximately, and for your max, you had 22.07. I'm going to write this in interval notation. So any values that fall within these values are usual. Anything that is outside of this would be unusual. So that's when we want to play around with the interval itself. So we see that 14.27 is the lower bound. 14, the value, the number of Americans out of a group of 23, 14 is not within the bounds. 14 is actually below. Okay, so 14 or less would be unusual. When we look at the upper bound, 22 is within the range, but 23 is not. So 23 or more would be unusual. So we can take one of two stances. We could say it would be usual to find that, 15 to 22 Americans out of a randomly selected group of 23 Americans would have a cell phone. You can say that it would be usual to have that value. Or you could say it would be unusual to have fewer than 14 or fewer, as well as 23 or more Americans out of a group of 23 randomly chosen people, Americans, to have a cell phone. So you can take one of two directions with this. I'm going to choose the usual values. It would be usual to find that 15 to 22 Americans would have a cell phone out of a randomly selected group of 23 Americans. And remember, you could have said it would be unusual to find that 14 or fewer or 23 or more out of a group of 12, or you could just say, or 23 exactly, would have cell phones out of a randomly selected group of 23 Americans. Excellent. What questions do you have for me? What can I help answer? While you're thinking, I'm going to write something on the side here that I would like you to write as well. Always include the size of the randomly selected group in your explanations. Okay, always include the size of your randomly selected group in your explanations. Because it's not like we're talking about 100 people, we're talking about a group of 23 people. So we have very different values when we change that n. Notice that our mean and our standard deviation depend on what n is, right? The mean is n times p. We're looking at groups of 23, but what would your mean look like if you were looking at groups of 100 people, right? It'll change. your standard deviation will also naturally change. Something to think about as you do this. Good. Having said that, that concludes our Unit 5 notes. So excellent work today. I'm going to stop the video now and we will come up with some due dates for Unit 5. Excellent work, everyone.